This is BlockFighting with a hooker, BlockfFghter2. So please join me in welcoming K2.
What's up, everyone? Thank you. DEF CON. Woo! Thanks, everyone, for coming. Everyone watching on DEF CON TV, I hope it's been a good time. The only problem I had so far was you couldn't get a beer this morning from the cafe. Beer sales were closed. So, no, it was, man, in the little cafe over there. But luckily, I don't know, I mean, maybe sort of luckily, my ex-wife is on the way over to give me a beer. Pretty lucky that kept it cool. Anyhow, enough of the drama and non-technical talk, I guess, but thanks again, everyone. You know, so this talk is going to kind of cover a bunch of different things in sort of a exception-based hooking technique. It's using capstone under the covers in various places, but I just committed the code. Oh, I thought this slide had the like GitHub on it. Let me go to the next one. So the neat thing about this hooking technique really is, in a nutshell, you know, tracing's great. You know, performance tracing is great, and you know, the kind of trace telemetry you get out of a binary when you're monitoring it, awesome for performance testing. And you know, the AFL guys, you know, the fuzzy lop, they use a lot of that kind of feedback to expand their algorithm based on that trace data. But there's a lot of looking at trace data, modifying your inputs, rerunning the binary from scratch. So you're kind of like constantly re-executing this binary all the time. But at least with this method, you're only going to execute one time. So you have all your state with you, and you're actually interrupting the execution, and you're able to make a decision based on, like, hey, do I want to emulate these instructions? Do I want to change what the program thinks it's doing? Do I want to sniff other aspects of it? And in this particular talk, so when I, you know, when I was thinking about what to do for these different block fighters, I call them, in a nutshell as well, the block fighters are, I'm talking about basic blocks. So like assembly instructions, these blocks that kind of, you know, are around the execution of your application that every time there's a conditional and a branch is taken, those are two new blocks that kind of fork off. So you've got these blocks, and we're going to fight those blocks. Some people call it binary steering or other things like that. You know, I've seen a lot of different trace or performance you know, explanations for, you know, getting coverage, you know, moving your coverage up. Static checkers do something similar in some cases for ensuring that they've tested all the code. And I'm sure all the DARPA stuff earlier, whoever saw all that stuff, this kind of fits into some of those aspects, but you know, the more tools, the better. And I can't tell you how many times I've been working on, you know, like a forensics thing or like an incident, and you know, I'm trying to use like whatever tool, and because whatever constraint of my environment and how this thing runs, the analysis method that I was previously, you know, super successful with wasn't working all the time. So, you know, it's always fun and good to kind of learn new things and to be aware of flexible or easy to use analysis primitives. So in terms of this method, I wrote 3 what I call block fighters. One is this ROP defender thing. So everyone who doesn't know what a ROP is return-oriented programming. There's also JOPs, jump-oriented, or LOPs, loop-oriented. I wanted to call it like drop defender, maybe. Joke? No? Okay. There's a music reference in there somewhere. I forget who the artist was who did that track. In any case, it's super easy to do this ROP protection. So kind of ad hoc, you know, maybe if you're deving an exploit or you're doing whatever, you're just tracing whatever, you want to understand the execution of something, you can use something similar to this ROP defender that I wrote to kind of understand where your ROP chain is breaking, or, you know, if you're defending something, maybe you want to like analyze an exploit and do whatever. I'll show you the code in a bit, but it's pretty fun and straightforward, kind of like the ROP defender itself is just like not even 20, 30 lines of code, to drop that in. The other thing I thought was kind of cool, it's just like a concept really, is everyone's talking about ransomware. Like ransomware is a big terrorizing thing and you're gonna steal all our money and everything. So I wrote this thing, this ransom escrow. So it will enforce key escrow of the encryption going on your computer so that, like, hey, if something's encrypting something on my box, I want that encryption key. Well, too late if you weren't watching where the encryption key came from, right? So this is a super simple primitive. It's on GitHub right now. I was going to expand it in a couple of ways, but I'll cover more of that later, or I'll talk about it as I do a little demo of it. There's a hypervisor DOS thing. It's cross-hypervisor. This is just something that came up while I was writing this tool, and I was like, hey, my friend was like, actually Rich in Seattle, he's doing another trace tool. It's very cool, run speed tracer. I've got a reference to it in here. He was doing this other tool, and he's like, hey man, why don't you do this in the cloud? I was like, yeah, okay, that's cool. Because the technique he was using couldn't work in the cloud because he was using these low-level performance tuning Intel features that aren't exposed to the hypervisor or whatever. So anyhow, the stuff in here in EhTrace is not as new, right? It's not like super bleeding edge. So there is kind of like sort of support for it in the hypervisors. Unfortunately, though, they all break. Well, except for, actually, I gotta take that back. The only hypervisor that has not fallen to its knees trying to execute this code is VirtualBox. So thanks, VirtualBox. I tend to, they're kind of like a whipping boy sometimes, but hey, got this one. Oh yeah, and there's some graphing stuff I did. If anyone's interested in graphing, I saw a lot of cool graphing stuff with these DARPA computers. I wanted to do this like 3D thing in the future. If you're into graphing and like computer visualization of code execution, let me know. I got some ideas I want to shoot around. Okay, yeah, hey. Whoops, I must have been just talking all over the place, but hooking, tracing. So tracing again, what's executing? The hooking, I want to modify it, right? Pretty simple, straightforward. We're going to talk about some various frustrations and hurdles, like the hypervisor DOS. That was kind of a frustration. I really wanted this to go cloud scale, but hey, maybe eventually when they get fixed, or who knows. And then also symbol support, I was going to have that in. I kind of backed it out because symbol handling is kind of a pain. Talk about that later. These are some other tools. Oh yeah, here's the GitHub. If you want to check it out, that's my GitHub. K2, really short GitHub username. Should be easy to remember. EhTrace, this other one, is the one we're talking about today. Invertero was the thing I did, started a couple years ago, DEF CON 22. It's like a nested virtualization memory, like recursive physical to virtual extraction thing. It's kind of neat. Oh yeah, anyone want to drop the code? Let me know if I forgot something. The good thing about what we've got here is it runs on bare metal really nice. It can run on a hypervisor. Probably VirtualBox is your best bet. And we're trying to do this binary steering thing. And what that means is, like, there are some things I have to do. Like, we have to reset the flags because the way this exception management works is the flags is reset every time in a different trap handler, like from the kernel when it calls us. So we got to like set that. So, if we see the binary looking for that flag set or unset, we need to either emulate that instruction or handle it in some way to neutralize it from detecting us. It's kind of like a classic sandbox problem. This might be kind of like a loose sandbox for all intents and purposes. There's obviously a lot of issues fighting code in your own address space. However, we are guaranteed certain things being in the exception handling path, in terms of state being synchronous. So again, yeah, there's some other DBI stuff. It's pretty cool. Totally want to check it out in the future. Some dreams for this stuff, lots more block fighters, fun little ideas. They're pretty straightforward to bang out. I mean, I did the ROP one in like 20 lines. I did the key escrow thing and, and the key escrow is a generic hooker for any function pre-post condition, which is great. The performance is kind of ranging. Slicing is your friend, and what that means is figuring out how to confine what you're looking at and not executing a bunch of random other stuff which you don't care about, right? So discounting stuff that you don't want to look at and figuring out what you want to look at, more or less. Water up here. Anyway, I do this on Windows X64, Windows 10. Other versions, your mileage may vary. This guy, Ferno, sorry if I'm bastardizing that thing, on the x86 SM net board from years ago, kind of reversed this technique and found it. And then, so you can check that out. And then this other guy, Laugh-Fool, showed me this other zip that you can do to patch and help make it work better on other versions of Windows. But thanks to those guys. Back in DEF CON 15, here's a paper, they're talking about covert debugging. Well, in a sense, this EhTrace stuff is sort of like an in-proc debugger. So all of our debugging happens in-proc in the same address space as what you're looking at. What makes it nice is that you don't have to use base pointers all the time. So like if you're logging the payload for the function call to this thing you want to look at, well, I don't have to rebase my pointer addresses because I'm in a different process and everything's mapped weirdly, and randomization of addresses is all the rage now. So by being in the address space of that process, you don't have to do like a lot of, I mean, it's not that hard, but in a sense, it just makes it super easy and straightforward to code naturally. Oh, thanks. Thanks, Allison. I like that. Thank you. She brought the beer. Woohoo! Wow. Cottonmouth. Oh yeah, some modern stuff. This Triton library from Quark's lab. This thing is super cool. If anyone's looked at it, this is like kind of like one of those ideal designs for DBI frameworks. It's got all these components to it. If you see in that example of tracers on the left-hand side of that block diagram, essentially we could fit in, or EhTrace could fit in place of any of those. So you can basically drop EhTrace in for PIN or Dynamo Rio or something. And in fact, I started to do that with an WinAFL port to EhTrace instead of using Dynamo Rio. But I just quite didn't get it all done. It's kind of in the GitHub a little bit if you want to look at it. I wanted to narrow down the slicing on it a bit more because obviously those are more mature tools and they have like focused right in on the DLLs, like the GDI plus test case or whatever for Dynamo Rio and WinAFL. It's just that one module, but I don't want to trace like NTDLL and all these other things. So it is what it is, but hopefully eventually we could get to decent performance level that it's not too bad to just use this thing for fun as well if you need to. It is really great as well, EhTrace, in that you don't need really to know much about the symbols, right? You're getting invoked by the system during execution, and all you really have to do is flip some flags and you'll maintain execution. You don't need to do any hooking, so you don't need to know the symbols, you don't need to know how many arguments there were. You really don't have to know very much at all, which is really great. And you get a lot of invocations, or you can tune that down. The disassembly, again, is, right now it's capstone based, which is a great tool. I really appreciate what those guys have done there, and I'm looking forward to their future releases. But obviously you're not going to want to do too much of that, so I'm going to want to try and do some kind of caching, and things get overly complicated the more you start thinking about it, like, okay, how am I going to defend against this? What am I going to do? Oh, I'll cache that result and that'll be fine. Again, this is just some background on hooking execution and instruction length decoders that go on, and hey, when there could be a new instruction set in that binary that prevents it from being hooked with your favorite hooker, so you're unable to like hook the execution of something, whereas with a model like this, you really don't have a problem. What's the problem? Oh yeah, debuggers are slow. And also, typically, when something wants to detect that it's being analyzed, like it'll do checksums on itself, hashes, like, hey, what's my checksum? Or maybe you're executing in like a secure environment, like an integrity mode OS that is like, hey, this DLL can't be changed, right? Well, then how do I trace the execution of that thing with these existing tools, right? What if I want to fuzz this thing, you know, in release mode, and I don't want to have to do a debug, and I don't want to have to do this, and, you know, I want to just trace what's going on right now, because anytime I alter anything about my test case, it stops reproing. So this is nice in some circumstances because you won't have to make as many changes to your test case or whatever you're doing to repro what you want, right? So we're not changing the code, we're not altering execution. So introducing some latency in the exception handler is not a big deal. I mean, what, people swap memory and this and that, right? It's not a huge impact to what a normal execution guarantee is for a binary. So they're just gonna kind of assume it's a slow box or whatever. You know, it just reduces the amount of problems you got to worry about. So these are some of the different things, some of the micro benchmarking. Total worst case scenario was 1,000%. So, sounds slow. But if you slice it up and you're able to have good checkpoints of where you want to enable and disable tracing, it's as low as 25%, right? It's just kind of, you know, it's impossible to have like the one method that does everything all the time. But, you know, hey, and then, you know, if we do some caching of inputs and we do understand the slicing of this binary and the, you know, we can understand, like, okay, at this point it's doing X, so we could just time warp, you know, or fast forward the state of execution to like this other checkpoint and skip something that might have been, you know, not really to worry about. EhTrace, so I'm partially Canadian, a boot, something else Canadian. Let's take the canoe. Woo! Anyhow, you know, I'll just throw that in there. Some of the other stuff we tried on the way to write this was kind of like stack hooking. And so one of the other concepts of, you know, so I said I had the BlockFighter. So with EhTrace, you can also essentially hook your tracing code. Your tracing code can be just a set of ROP gadgets or LOPs or JOPs or whatever the heck. It's just a function pointer that gets called. Since you're not making any changes to these binaries, you're actually just getting like inserted into the stack, and you can manipulate the execution without worrying about introducing unsigned code and these kind of issues, or you know, whatever else it might be. So it's kind of fun from that aspect as well. And if you want to go ahead and bang out like you know, a crazy, you know, backdoor or whatever else, you know, hey, there's some ROP backdoors or ROP malware I've seen floating around. Or if you want to trace those things, you can use this as well. It's kind of fun. It's very flexible. So I guess one of the ideas is anytime you make like an offensive thing, you always got to remember to pair it with like a countermeasure. So there's a lot of like measures and countermeasures in analyzing stuff, right? Like, okay, well, you know, I'm going to analyze it by extracting the state, you know, whenever it crosses the kernel. But then, oh, okay, well, it repairs itself before it calls the kernel and make it look normal, right? So it falls within these normalized assumptions. You know, who knows, right? There could be a lot of different ways to counteract or act. You know, when you're talking about trying to understand this like huge amount of state and this huge amount of moving parts in binary execution. And I guess as we get to the demo of the hypervisor thing, that's kind of like an explanation of why all these hypervisors are DOSed from this thing. It's like, well, there's a lot of state moving around, and no one's hit this path before, and it's really expensive, and it doesn't matter how many CPU cores you have, it'll just take you down if you're not efficient overall. So anyhow, yeah, the stack hooking, in the end, I might do some kind of hybrid technique, because if I'm hooking the stack directly, by theoretically chopping in an exception, manipulating the stack, and then executing. I'm thinking about using that as a mechanism to turn this on and off dynamically. So obviously that'd be a lot faster to kind of, trim down your exception handling. This is how it works, super easy. This DR7 thing, this is like, I guess, a backdoor that Fenro found. So this is typically not a register that you can affect from user space. This is like a kernel-only thing. The debug MSR right there. So this DR7 actually weaves its way back into the debug MSR, and that's why if you don't have Windows 10, so this works great in Windows 10. Other people have gotten varying reports. But if you're not using Windows 10, like 2008 or whatever it is, you got to go to /debug, and then I do the MSR right for you, but you don't need to, right? So when I do the demo here, it'll just be user space. You'll even see the warning, hey, this thing didn't work, and it obviously does. So the ROP hook idea, kind of fun. What else is it good for? Basic block, coverage, back into DBI. Try not to emulate too much. I'll be working on some new updates for caching or making it better based on what people think and what they'd like to see. It infuriates me to no end every time I go to get my favorite tracing tool when it doesn't have the capability to trace the version of the OS I'm using, and I got to do the symbol thing or manually edit. There's a lot of times there's like so much rigmarole just to start doing what you want to do with certain types of hooking. Having the flexibility to use this technique has really helped me out in analyzing binaries in execution environments that were really confined. So maintaining control, I mentioned it before, there's the flag register, but there's other things that you want to do. You want to make sure no one's like taking over control of the EH. Like if you're going to go ahead and build like a whole sandbox around this, hey, go for it. But that's like a very long war you're going to have to fight. Of course, Street Fighter 2, everybody. Yeah! Our new game. Woo! I was really good with Ken myself. I like the uppercuts. These are some comments on like other areas that I need to like flesh out, or if you're going to do some kind of like analyzing malware or whatever, like sandboxy stuff, some things to think about, where you would want to do some monitoring to make sure you're not being desynchronized from the execution. Branch stepping is great. However, in the end, if we do there are these like ROP jitters, kind of also I've seen a lot of them like capstone based as well, like ROP jitters and different types of jitting. If there was like a loop-oriented programming jitter, I think the performance of this thing would be like near native, so it would be great. I mentioned some of this stuff. The ransom warrior. Here, I'll fire this guy out. You let me know what you think. Okay. Oh, my projector is not. Hold on. Let me kill Outlook here for a sec. Whoops. Okay. I think I can see. Okay, so this thing here, the code for this is just going to do standard crypto calls. I canned it. There's a static lib I use for test cases so I don't have to like race the injection of the DLL and all this kind of stuff. Anyhow, when we execute this, this is like crypt gen random being called. This is the data that was actually exfilled in EhTrace through the exception monitoring of the execution, through the code analysis, or block analysis rather. And then, this is like the return value from the program. So like, the post condition on that hook, like hooked and logged the incoming random data before the return, which is great. So we know we're at a really good place to egress this information to like a network server, or if there was some kind of like hypervisor enclave, like protecting my secrets and stuff, I could be like, oh, send this over there. This is some bits that I might care about in the future. If I'm and I'm, if I'm gonna get ransomwared, I could unwind that spool of bits and say, hey, are any of these used in my crypto key? Luckily, with crypto functions, even if the ransomware has like got this static lib of like OpenSSL built into the binary, I don't know if everybody knows, but a pretty good technique for finding in crypto functions is constants, because everyone wants to use like standard cryptographic APIs and whatnot and functions that are provably secure in one way or another by math people. So even the bad guys want that, so they're not going to be shipping their own stuff. So if we're able to raise the bar in monitoring the crypto and monitoring the execution of anything that's going to try to do any kind of crypto op on your box, well then, hey, now they're going to have to either roll their own or, which will probably be something that'll be crackable, give us some lead time to get everybody, just saving all their data in the cloud, right? So, yeah. I mean, the cloud's great, I'm sorry, but I love the cloud, actually. Love-hate relationship. Okay, so that was a key escrow. Now the ROP stuff is super straightforward. I'm just going to show the code. It's in here. ROP Defender. So that ROP Defender was actually executing, so they're all like chained together. So this ROP Defender is running at the same time as the key escrow guy as well. The perf overhead, once you're already done the exception pump, you can do a lot. you've already spent the cycles, so you can do a lot of stuff, right? You're not, you've already taken the hit. You might as well do 10 things or 100, it doesn't matter. So this kind of ROP defense stuff was like a few years ago. People were talking about this, like K-bouncer and these things. This is some code. Lots of people had like, hey, let's pair these things up, right? If you're doing a ret, there better be a call instruction that's paired with that ret, or else it's invalid. So let's reduce the gadget space. So that's when everyone started to talk about, oh, let's do lops and jops and dot drop. So that one's pretty straightforward. And it's cake. You just go, hey, what's the RSP and whatnot. And yeah, you'll see things, if anyone's like a major coder and wants to get involved, you'll see things like, hey, the stack pointer is really nice to have because you can understand the depth UR and everything else. Okay, let me get my state here. That was that one. Hold on. There we go. So yeah, enforce cryptographic key escrow. Good idea, I think. I want to know what's encrypted on my computer. Coverage. Can you hear me now? Right. I guess he switched networks. Flame graph. So I did a bunch of different graphs here. Here's one. One of the issues with this much data, though, you can imagine if I'm logging every basic block that's executed in this binary, there's so much data, like how are you going to visualize that? Turns out, really hard problem. That's why I got some 3D ideas coming up, but these are 3 different graphs that are already built in. I did it with like WPF and Microsoft AGL. I actually got a bug on the MSAGL guys. As soon as that comes in, there's going to be a much cooler graph, which is called a graph map, and it's all navigatable and expandable. And you click on this block, and it'll be like, like a spider web kind of blowing up. It's kind of nice. But they depend on this like janky EDU like university guy thing that's like hasn't been updated in like 15 years, and they're just like, just wait, it's almost fixed. I'm like, okay, thanks for making it free. Oh yeah, here we go. So this is a flame graph. So all of these graphs are actually generated with just the stock data that's logged in the logging function, which is just, you know, it's a fairly limited amount of bits. It's about 128 bits per block. But this is kind of like the stack depth over time, and then per block. So there'd be like 3 or 4 blocks horizontally at the same stack depth. That means that that function had 3 blocks, right? And then you see the ones with just 1, that was like a leaf or just like a single call or something. But, you know, that's kind of how that thing looks. Unfortunately, like the Perl scripts that are used to generate this stuff were like generating like gigabyte files and stuff, so that was kind of, you know, needed to really trim that down. So again, the symbols are coming. I'm also kind of waiting on Microsoft's PDB to be, their GitHub to be fixed up a little bit. It looks almost ready too, so. It's coming, source code commit's coming. You know, some different stuff. Have fun, you know, try and do your own thing. You know, there's a lot of kind of just hints at what to do and like different ideas. I'd love to like engage people on different concepts of like analysis and modeling and just kind of understanding and comprehension of what's executing. Feel free to like shoot me an idea of something you want me to do or think about. Okay, here, I'm going to do the hypervisor one. Could I get the thing reset? Hold on. Okay, cool. This aprep here, this exe is like from the repro, and I committed this stuff before I realized the effect of it or how far wide-reaching it was. So, you know, one thing, like if your code, like, you know, I've been kind of jumping back and forth between the good and the bad and the evil versus good a little bit here, code versus code or, you know, whatever, us against the robots or something. This code here, you know, so frequently if you're in a hypervisor, you're not going to want to execute maybe, or if you're being virtualized or emulated, you don't want to execute necessarily. So to have a neat little, you know, tiny amount of code like this that can tell you right away, hey, something, you know, you're being looked at or you're not in a native execution context is nice, you know. Or, you know, if you just want to DOS some infrastructure, I guess that's possible. Some people like to do that. The fun thing is here, so the CPU utilization in the user space VM monitors goes up to like 100% per thread you give it. So I gave this 8 cores. Certain hypervisors have additional overhead behind that on the kernel side, roughly 10%. So you can imagine if a cloud vendor hasn't necessarily planned for that excess capacity, they may be negatively impacted if this is going on like crazy on their box, right? If they've overcommitted resources. I was really tempted to run this. I saw a couple times the CPU utilization like up over like, even just one CPU was like, it'd say like 350%. And I was like, oh man, did I overflow something in the percentage? Are they gonna pay me now to like DOS their infrastructure? That'd be kind of cool. So the CPU there is at 12. Bad at my swipes. Where's my mouse? There we go. So I don't know if you can see that. I think it says 760%. And oh, you can see the graph at least. The graph's up pegged. So it's kind of neat. It's kind of easy. So with just one thread doing this, it's like killed the box. Cool. So it doesn't matter how many CPUs you give this thing, with just one thread, we're going to kill it. So that's kind of fun. Feel free to figure out what's going on, because it's kind of like affecting different things. But you know, emulation of a CPU is kind of a complex thing, and with this tracing stuff is what we're talking about as well, is that you know, either emulating or fighting the block to maintain control or maintain your understanding of what's going on is not the easiest thing in the world. So as stuff gets more complex, you're always going to see these, you know, these sort of things kind of creep in. Basically, if anyone has any questions, probably wrap up pretty quick here and talk about it, or see any of the other artifacts we're doing. Thanks again for coming. Let me know if anyone has any questions. Give you a couple minutes, think about it. Perfectly explained. I love it. Every time. Oh yeah, hey. Sure, dude.
So for crypto identification, apart from constants,
Yes.
have you looked at identifying blocks of code? So say, like, if I look at the disassembly of an RC4 function, or well, leading up to an RC4, you see the key stream generation stuff. Like, have you looked at how you'd be able to identify those in line?
You know, well, the cool thing is, if you're doing the logging, you have this like block level telemetry coming from the app. So you could do some post processing, like some of the perf guys do, with feeding the, you know, an understanding. But you know, that might slow it down a lot at runtime, because I mean, with like RC4, it's kind of like a simple set of operations, right? Like it's not like overly complex. You can like mask those pretty easily. But in terms of like what the RC4 is using for its, you know, basis, you know, vis-a-vis what is the key that it's using, the input, you know, if it's not able to access random, you know, if we remove its entropy sources, then it's maybe not as important to know that per se, because then we can understand, hey, this thing, it has a limited set of keys now, right? It's possible outputs is X, you know? So yeah, something like RC4 will be a little bit tough, but you know, maybe you could do it with some of the graph detection. But in the end, hopefully, by understanding the inputs and reducing the entropy, I hope to be sufficient in some ways. You know.
Cool. Thanks.
Cool. Thanks. Good question. Thanks. Awesome. Anyone else? Jump around. Well, hopefully we won't have any more ransomware next year, so we'll all have backup keys, right? You know, I'd really appreciate that. Or insurance, I guess. Cool. Thanks again, guys.